Organic chemistry. For a lot of us, just hearing that phrase brings back some, stressful memories, right? Late nights, endless flashcards, and what feels like a mountain of reactions to just cram into your brain. But what if I told you it's not about memorization at all? What if it's really about seeing the hidden patterns? Let's unlock them. I mean, this is the number one question, isn't it? The biggest frustration. It feels like this endless, random list of disconnected facts. You learn one reaction for one molecule, and then the next one seems totally different. But is that really what's going on? Well, here's the secret. Organic chemistry is really just a giant puzzle. And like any good puzzle, it's governed by just a few powerful recurring principles. Once you see the patterns, all that memorization just kind of disappears, and it becomes a game of logic. And in this explainer, we're going to hand you the keys. All right, let's start with our first master key, the electrophilic addition reaction. Now, electrophilic sounds fancy, but it just means electron-loving, and we're about to see exactly why that matters. This one single pattern is the key to understanding how two huge families of molecules react: alkenes with their double bonds and alkynes with their triple bonds. This right here is the core idea. A double bond is packed with electrons. It's electron-rich. That makes it a nucleophile, and it's naturally drawn to anything that's electron-poor, an electrophile. This fundamental attraction, this pull, is what drives countless reactions. And it all happens in this beautiful two-step dance. First, the pi bond, with all its electrons, attacks the electrophile. This breaks the pi bond, but it leaves one of the carbons with a positive charge. We call that a carbocation. So what's step two? Well, a nucleophile, like the bromide ion that got left behind, sees that positive charge and captures it. Attack, capture. That's the pattern. That's the dance. Okay, so you might be asking, where exactly does the electrophile add? This brings us to Markovnikov's rule, which you've probably heard taught as the rich get richer. The hydrogen adds to the carbon that already has more hydrogens. But listen, this isn't just some arbitrary rule to memorize. The crucial part is why it happens. It's because that specific pathway creates the most stable possible intermediate. And this is that why. Carbocations are unstable, but they can be stabilized by their neighbors, the carbon groups next to them. A tertiary carbocation, connected to 3 other carbons, is the most stable. It's getting the most help. A primary one is the least stable. And here's the thing about reactions. They're kind of lazy. They will always try to go through the most stable, lowest energy pathway possible. That's why Markovnikov's rule works. It's not magic. It's just stability. Okay, so now we understand the default pattern. We know what the reaction wants to do on its own. But what if we don't want the default product? This is where organic chemistry gets really powerful. This is where, by choosing our reagents, we get to be the director of the reaction. Let's see this in action. Say we want to add water across a double bond to make an alcohol. If we use simple acid and water, we follow Markovnikov's rule. No surprises there. The OH group adds to the more substituted carbon. But check this out. If we use a different set of reagents, this is hydroboration oxidation, we can actually force the OH to add to the less substituted carbon. See that? 2 different sets of reagents, 2 completely different products. You are in control. Here's another classic control problem for you. If you just add regular hydrogen gas to an alkyne, it doesn't want to stop. It'll reduce it all the way down to a single bonded alkane. But what if you want to stop halfway? What if you want the alkene? How do you do that? Well, if your goal is a cis alkene, that means the hydrogens end up on the same side of the double bond, you use a special tool. It's a poisoned catalyst called Lindlar's catalyst. Basically, it's just reactive enough to add 1 molecule of hydrogen, but it's too weak to go any further. And because the reaction happens on the flat surface of the catalyst, both hydrogens have to add from the same side. And just like that, you get your cis product, specifically. So what if you want the trans alkene, where the hydrogens add to opposite sides? You guessed it, you just switch your reagents. A dissolving metal reduction, using sodium in ammonia, goes through a totally different mechanism that adds the hydrogens to opposite sides of the bond. Again, your choice of tool directly controls the geometry, the shape of the final product. It's beautiful. Okay, now let's start to see how all these principles create a giant web, connecting all these different types of molecules. The skills you learn for alkenes don't just exist in a vacuum. They are absolutely the key to understanding other functional groups like alcohols.
So here's a super common issue. If you want an alcohol to react, you often need that OH group to leave. The problem, hydroxide is a really strong base, which in the world of organic chemistry makes it a terrible leaving group. It just does not want to go. So how do we convince it? We trick it. By adding a strong acid, we protonate the minus OH, and suddenly it's not minus OH anymore, it's minus H2O. It's water. And water is an excellent leaving group. It leaves, no problem. And what does it leave behind? Our old friend, the carbocation. And we know exactly what to do with those. A weak base just comes along, plucks off a nearby hydrogen, and those electrons snap down to form an alkene. We just used our knowledge to turn an alcohol into an alkene.
We've seen how to change functional groups, how to control geometry, but now we're talking about the true holy grail of organic synthesis, creating brand new carbon-carbon bonds, literally building bigger, more complex molecules from smaller pieces. And this is one of the most elegant ways to do it. The hydrogen on an alkyne at the very end of a carbon chain is surprisingly acidic. That means a really strong base can come in and just pluck it right off. What you're left with is a carbon with a negative charge, an acetylide iod. And this thing is a powerhouse nucleophile. It can then go and attack an electron-poor carbon, forging a new carbon-carbon bond. I mean, this is basically molecular construction. So let's just zoom out for a second. We haven't just learned a random list of reactions here. What we've really done is assembled a toolkit of fundamental principles that you can apply to solve totally new problems. So here's the core of it. Number 1, pi bonds are electron-rich and they like to attack things. Number 2, reactions always take the path of least resistance, which means they go through the most stable intermediates. 3, you, the chemist, can control the outcome just by choosing your tools, your reagents. And you can even do some pretty amazing things, like turning a bad leaving group into a good one, or forging entirely new carbon skeletons. And this really is the ultimate takeaway. Every complex synthesis, every new reaction you ever encounter is built on these foundational ideas. It's a language of electrons and stability, not a dictionary of facts you have to memorize. So the next time you look at a molecule, don't just see a drawing. See the puzzle, see the possibilities. You have the tools, you know the patterns, so the only question left is, what will you build?